So hi everyone, I'm Chang from University of Virginia. Today I will talk about detecting silent failures in distributed systems. Specifically, we will introduce a new technique to automatically derive runtime checkers from tests. Distributed systems today have many semantics exposed through client APIs, component guarantees, configurations, etc. New interfaces and semantics are also continuously introduced as the system evolves. Users and other systems, they heavily depend on their correctness. So if the systems silently break their semantics, that can cause catastrophic consequences. For example, Zookeeper is a popular distributed coordination service. A key feature provided by it is called ephemeral node. It allows you to create a node that can automatically delete itself once the sessions disconnect. Node here means a data record. So developers often use this as a feature to implement service discovery. Other services like Kafka, a streaming service, can conveniently register their address in Zookeeper. So as long as their servers are alive, the address will be visible in Zookeeper to other clients or systems. If Kafka instance crash, the Zookeeper guarantees that those addresses will be removed. For such failures, for such semantics, a non-silent failure would be Zookeeper is down and the client receives exceptions. It's bad, but at least the clients know something is going wrong. But client wouldn't know when silent failure happens. In a production incident, after Kafka instance crashed, its associated address still exists, even though the session that created them was long gone. As a result, the clients were confused. They kept trying to connect to the crash instance. And since Zookeeper is often used to maintain metadata for other distributed systems, such incorrectness will propagate to other applications. And similar silent failures are behind many real-world incidents. Recent studies show that they can take up to 39% of all studied failures. And they come from not just software bugs, but also Mercury CPU cores. There is a pressing need for systems to go beyond just monitoring statistics, but verifying whether the semantics is violated at runtime or not. Central to this is a set of semantic checkers. Of course, writing semantic checker for large distributed systems is not easy. Prior work, they focus on checking well-defined properties like, for example, consistency of distributed log. But the systems we target have abundant, loosely defined semantics. To map them to a concrete, correct checker, we need to deeply understand the system code and behavior to decide what needs to be checked, what can we expect, and when should the checker be triggered. So we ask, is it possible to automatically generate such checkers? Actually, distributed systems today have abundant test resources. This is a test from Zookeeper that simulates the node creation and session disconnection, and assert if the ephemeral node exists. They are valuable information for runtime checking. There have been works that infer likely invariants from the test traces with statistical method. Daikon and Dinf, they infer system variable relations based on test traces. A more recent work, Zookeeper infers event relations from past failures. Yes, they can generate useful rules, but these inferred invariants are usually too simple and not expressive enough for complex semantics. And many of these inferred invariants, they are false due to the inaccuracy in statistical inference. Instead, we propose to directly transform the test code into semantic checkers. Since the tests include carefully designed workloads and semantic-specific oracles, aka assertions, which are currently not fully leveraged in the existing solutions. Our idea is to reuse the checking-related logic and turn that into a parameterized checker function. And we want to extract the precondition from the test workloads and generalize so they can be applicable to production workloads. Then the generated checker will be deployed with the target system together at runtime and activate on the production workloads. Before we rush to start coding and implement the idea, we took a step back and see if this approach is indeed feasible. We conducted a large-scale study on 210 test cases collected from 6 distributed systems. For each test, we asked several questions such as, do the tests contain useful semantic checks? And is the checking logic really generalizable? Interestingly, we found that many test codes in practice, they have a clear pattern for transformation and generalization. First, most of the tests, they use standard assertions such as assert true and assert equals. The remaining tests that without assertions, they are usually performance benchmarks. And these tests have many useful utility functions. This is a class from HDFS, which includes dozens of utility functions from checking file correctness to verifying the cache usage. Including them in our checkers can save many implementation efforts. Second, we found that it is common for expected value in assertion to have simple relations with prior workload values, such as equality. This means we can potentially infer the assertion values from the past events. And we found that in 2/3 of the tests, the checking logic can be generalized from the test to production by replacing specific instances. Based on these findings, we designed a tool, T2C, to automate the checker construction. For a given system, T2C leverages a combination of static and dynamic analysis to transform existing test code into reusable semantic checkers. It mutates each checker to more variants, so it covers a broader range of the cases. At the end of generation, the system includes a multi-level validation step to ensure the generated checkers are indeed valid. And in the production phase, the generated checkers are deployed together with the target system to continuously monitor the silent failures. I will walk through this process step by step in the next few slides. The first step is to extract the checker function. A test case contains many instructions, and T2C is most interested in extracting the checking logic. This is another test example from HDFS, which checks if a snapshot file remains unchanged if, say, hey, we append more contents to the original file. The test oracle is in line 15, which depend on several other instructions. T2C uses static slicing algorithm to encapsulate this instruction into a standalone checker function. It starts from this assertion and identify all the values used in the expression, which include two workloads with variable original len and the data from snapshot. The algorithm's goal is to identify how can we construct these workloads for runtime checking. And it keeps traverse backwards, analyzing each preceding statement. The algorithm will find out data from snapshot is generated by a function call, read file buffer. Thus, the algorithm would mark this statement to include in the checker function as well, and add its parameter to the checking set instead of the original data from snapshot. This process will continue until the start of the test is reached, and eventually marks all the related statements to include, as well as a list of parameters for this checker function. And T2C extracts the instruction into this standalone checking function, and it automatically fills in the missing parts, such as variable initialization, type conversion, and also handling name aliases. The algorithm handles special cases such as excluding the side effect operation using a purity analysis. So our checkers would only observe, not modify the system states. There are more details about our algorithm in the full paper. Then the next question is, now we have this checker function prepared, but how do we calculate the parameters in the production runtime? In the offline phase, T2C uses dynamic analysis on test code to derive concrete preconditions first. It instruments the system interfaces and then executes the test code so it can obtain an ordered sequence of system operation invocation, each with concrete arguments. And this precondition is tied with specific test workloads. So T2C further symbolizes the concrete values by identifying the constraints among them. Of course, this is challenging in the general case, but fortunately, our finding found that there are many values in the test have simple constraints, such as equality or contains, which are relatively easy to infer. And when encountering a concrete value in a clause that is equal to earlier value, T2C would assign them with the same symbol. It auto outputs the other supported relations in the generated constraints field. And then in the production, we can similarly dynamically instrument to emit system traces and compare the production traces with the symbolic precondition we have to calculate. Here now, if we want to invoke the checker function, what concrete value should we use to activate? For example, in this case, the symbol 1 value should be production 1. The generated symbolic precondition can still be too restrictive. So T2C further relaxes it with 4 types of mutations, such as reordering 2 adjacent operations. It enumerates different mutations of the precondition in a bounded way and generates variants, so checkers can support a broader scenario. You may ask, hey, what if the generated checkers or the variants, they are incorrect? Indeed, that's why T2C uses 4 levels of validation to prune out the invalid checkers. The first being the compilation to ensure the syntactic correctness. And the second level is to ensure the checkers is roundable via the JVM verified sanity checks. The third level is more like interesting self-validation. Essentially, T2C would replace the original test assertion with the generated checker and reruns the modified test. Failure here would mark the checker invalid. And lastly, T2C cross-validates by simulating a pre-production environment. It runs each checker against workloads from other passing tests, so we can remove those over-generalized checkers. In production phase, T2C deploys the validated checker with the target system. And the T2C has a runtime library that continuously evaluates the checker's precondition and its constraints against production workload and invoke the checker function accordingly. It uses a circular buffer to manage the maximum memory usage, so we don't want any excessive GCs here. It automatically discards the expired traces. And it employs a precondition index with a tree to efficiently match the traces with precondition, so we don't need to traverse the checkers one by one. Now let's talk about evaluation. We applied the tool to 4 popular distributed systems, Zookeeper, Cassandra, etc., and successfully generate hundreds of checkers. The checkers here will only be activated if their precondition matches during production runtime. And to evaluate the effectiveness of our generated checkers, we reproduce 20 real-world silent failures. We compare the results with T2C with other 3 types of advanced detectors. So besides the DINF and OSDI we introduced earlier, we also designed a new type of checking method, in vivo checker, which redirects the test workload and assertions from simulated test instance to production server instance. so it can expose some interesting issues. As a result, T2C detects most of the failures, in total 15 cases out of 20. The tests T2C used to generate the checkers were added a long time ago, on average 4 years by developers before the failure happened. And in comparison, even the combination of these baseline checkers, they can only detect 8 cases. We found that T2C is particularly effective in detecting cases that require fine-grained assertions. And those failures we missed are usually because they do not have a good quality of the test. So they are still likely detectable if the developers improve the test quality. T2C even exposed a new bug in the latest Zookeeper. Essentially, under the network faults, we found that sometimes from nodes, they show inconsistency between different nodes. And T2C provided traces to help locate the root cause. We have reported this bug to the developers. We also measure the false positive of the checkers with Jepsen, a popular distributed testing framework. And T2C generates a low false positive compared to the baseline checkers, all thanks to the validation mechanism. We also measure the runtime overhead with YCSB benchmark. T2C generates a 4% throughput overhead on average. The generated checker, they typically have precise and complex precondition. Thus, they are triggered less frequently and incurs less overhead. Now I conclude this talk. Silent failures are severe threat to cloud system availability, and test cases contain valuable information about system semantics. In this talk, we introduce T2C, which derives semantic checkers from tests to detect failures, and our evaluation shows that it can detect real-world failures with a small runtime overhead. And as a follow-up work, we plan to explore using LLMs to infer the semantic meaning of those tricky magic values in the test that give us most headache to generate more accurate and general runtime checkers. We look forward to sharing our findings in the future. Thank you so much for listening.